Welcome, everyone, to the 2025 Vision Spectra Conference. Thank you all so much for joining us. And in this session, you will hear from Mike Walters, Vice President of Product Management for Emerging Products at Teledyne FLIR. Mike earned a master's degree in electrical engineering and has spent over 35 years in the industry. Today, he joins us to discuss how IR sensors are playing a key role in meeting new federal motor vehicle safety standards.
Sure. So what is the problem that we're trying to solve? And this slide really illustrates the problem. If you look at the blue trend line here on the right side of this chart, it shows the trend for pedestrian deaths in the US over the last 25 years or so. And what you'll notice right away is while in the rest of the world, pedestrian deaths are actually declining or holding stable, in the US since about 2007, we've seen an ever increasing upward trend in pedestrian deaths. And in fact, tragically, about 7,000 pedestrians are killed each year in automobile accidents. There isn't complete agreement on the causality of this upward trend in the US, but the general consensus is there are a couple of major factors. Right around 2007, smartphones were introduced, so we started to have these very enticing, attention grabbing gadgets in our vehicles. And then the trend in the US, we tend to drive larger vehicles, so SUVs, trucks, and the like. So when we're distracted and we lose sight of the roadway and have a collision, unfortunately, the results are much more deadly. So that's the problem that we're trying to address. And one other thing to note is about three quarters, 75% of these pedestrian deaths occur at night. So wouldn't it be great if we had some kind of vision system that would let us understand our surroundings in the vehicle at night? This is perhaps an even sadder histogram. This histogram shows the distribution of pedestrian deaths and versus the miles per hour that the vehicle was going when the collision that resulted in a death happened. So you can see relatively few fatal accidents are occurring below 25 miles an hour. And then, as you would expect, as we're traveling faster, when we unfortunately have a vehicle and pedestrian collision, the results are more serious, resulting in a lot of deaths. Now, previously, the current regulations on automatic emergency braking. So that's when the vehicle detects something in the pathway, like a pedestrian of the vehicle, and automatically applies the brakes to avoid the collision or to reduce the lethality of the collision. Current regulations call for this automatic emergency braking testing to happen in daylight and happen at speeds of less than 25 miles an hour. So you can see that unfortunately the current regulations, they're a big step forward over not having any automatic emergency braking at all, but they're really covering a space where not many fatal accidents occur. The National Highway Transportation Safety Administration, or NHTSA, is aware of these statistics. They're compiled each year. And last year, based on the trend you saw in the previous slide and this data, NHTSA basically upped the requirements that will come into effect in 2030 for this automatic emergency braking testing to happen at speeds up to 40 miles an hour, so saving a larger number of lives. They also notably required that the testing be conducted in real world situations, so in both daytime and nighttime, where the fatalities tend to happen. So a giant step forward. In our response to the NHTSA proposed rulemaking process at Teledyne FLIR, we actually proposed that the speed of the test be greater. And that's something we'll probably see as we continue to advocate for that, to basically um, move it toward a situation where there are no motor vehicle pedestrian fatalities, or zero fatalities as it's known in the industry. So what is a thermal camera, and how can a thermal camera help in this situation? Well, first of all, a thermal camera is looking out in the far infrared portion of the spectrum, so out in the 8 to 14 micron wavelength range. Our eyes see this rainbow part of the electromagnetic spectrum that's something like 0.4 microns out to 0.7 microns. So that's what our eyes see, but we're actually looking further out in the spectrum in this 8 to 14 micron region, and we're actually seeing and imaging heat that is generated by all terrestrial objects. So everything we see around us on the Earth is emitting a heat signature, and that's what we're able to see. This heat signature gives us the capabilities that are shown on the bottom of the slide. Most crucially, we're able to see in total darkness. So that addresses the space where 3/4 of the fatalities are happening at nighttime. Interestingly, we're also able to see through most smoke and fog. It's a very common application of thermal imaging for firefighters to use a thermal camera to find their way in and out of smoke-filled buildings, to find and rescue any occupants of those buildings. Since we're looking at heat emitted from the objects, we're actually able to measure the temperature of the objects without touching them. So this is very useful in industrial and process control applications. And then because we're out at these longer wavelengths, 8 to 14 microns, and we're only relying on the heat to travel from the object to the thermal camera, a shorter path, we're able to achieve very incredible long range imaging. And even though we're looking and visualizing heat, our data presents itself very much like a visual camera data. So we're able to leverage machine learning and recognize and classify pedestrians, bicyclists, and the like. So these are the features and capabilities of a thermal camera that I think it's pretty evident how this can address the problem of nighttime fatalities. So just to drill that point home a little bit more, these are the basic ways we can apply thermal imaging, machine vision to making automobiles and roads safer. In the left-hand column on this slide, we have visible images. So this is what your phone camera would see. This is what your eyes see. And on the right-hand column, we have the thermal image. Now, it's important to know we're not actually seeing colors. So in these images, we're mapping heat or temperature to colors. And in this case, what we call the color palette, or the artificial color palette, is what we call white hot. So parts of the scene that are hot, like people, you see in this image as white. Of course, it's just bits for the machine learning, and the visualization doesn't matter so much. But in for comparison purposes and to understand, we use these different color palettes, and they're also used, of course, when humans are interpreting the images. So in this first scene at the top, we have a community bike ride in Santa Barbara, California, that happens regularly. And you notice what your eyes would see and what the visible camera sees. There's a lot of glare in the images from the street lights, the headlights, and it's really hard to tell how many bicyclists are on the left-hand side of the image. The thermal camera is not impacted at all by the light from the street lights or the headlights. So you can see that it's very easy with a thermal camera to pick apart the scene and distinguish the bicyclists that are riding along the road. You detect vehicles, and really you have a whole lot of information about the scene from the thermal camera. And once we start thinking about thermal cameras and night vision, you'll see the same thing in the daytime. So it's important, as you see in the middle image here, that thermal cameras are also a powerful technology for improving the vehicle situational awareness in both the day and nighttime. So in the daytime, if you're driving into the rising or setting sun, uh, when we're doing that as humans, we're shielding our eyes, we're putting down the visor, and we really lose a lot of visibility in terms of what's ahead of us, and tragedies can happen in this kind of situation. Somebody crosses the street, you don't see them, and tragedy results. With a thermal image, since we're looking at heat, not light, the sun remains a disk in the sky. So it's very easy to have very good situational awareness. And that's another value we think that thermal imaging brings. We really believe in this suite of sensors or sensor fusion where you have visible cameras, you have radar, you have thermal cameras, and it's really the intelligence of this fused sensor system that gives you vehicle safety that it exceeds what a human can do. And then last on this slide, we have a drive along the beach on a foggy night. And, in a fog, as humans, it can be very difficult to see our surroundings. And the thermal image that's using these longer 8 to 14 micron wavelengths is very capable of catching the pedestrian, especially if the pedestrian is about to cross the road in front of you, or um, we have lots of foggy situations in California, and often there can be multi-car pileups. So a thermal imager is very useful in these types of situations. So essentially, a thermal camera gives you greatly improved situational awareness for the vehicle. It complements some of the things our eyes or a visible camera would do. And I think you get the idea of how it can be used to make a vehicle safer. So along these lines, to address this opportunity at Teledyne FLIR, we've been shipping thermal cameras into automotive applications for the better part of 2 decades. But as we move into actually having the camera control the vehicle, we created a automotive purpose-built thermal camera so that we could safely have the vehicle use this information to apply the brakes and control the vehicle. That automotive safety process is used in it's used in visible cameras. It's called automotive safety integrity level, or ASIL, and we created the world's first ASIL-B thermal or long-wave infrared camera. It's a very sensitive camera. It's in a rugged, environmentally sealed package that can be safely mounted on a vehicle. We have no shutter in this camera. Often thermal cameras have shutters to clean up the image. Our processes have improved, and we no longer need that mechanical shutter, which can be an item that could fail and render all these benefits of a thermal camera unfunctional or require replacement on the vehicle. So shuttleless is very important for high reliability. And we also have a defrost function built in. So if you have frost accumulating on the front window of the camera, we can clear that up. So we're getting very good imagery. So we wanted to put this automotive specific thermal camera to the test. Would we pass these new um, National Highway Transportation Safety Administration proposed tests that are specified in this Federal Motor Vehicle Safety Standard 127. So working with a partner, VSI Labs, we outfitted a Ford Fusion with the automotive specific thermal camera, a visible camera, and a radar system. And we fused these sensors together to apply brake-by-wire on the vehicle. We wanted to also at the same time benchmark current vehicles on the road. So we tested a Tesla Model Y, which uses visible sensors. We tested a Subaru, which has stereo or multiple visible cameras, very much like our eyes. And then we tested a Toyota vehicle, which uses a combination of visible cameras and radars. And the dots at the bottom of the slide just give you a look at the scene. To test a thermal camera, as I said before, we're looking at heat. Humans have a very strong heat signature. So you see a couple of our team that are standing on either side of a soft pedestrian target thermal dummy. So this thermal dummy is actively heated to mimic the heat signature of a human for the testing that we performed. The test conditions that NHTSA has specified in this FMVSS 127 are shown here. They're pretty standard real world type of situations. You have a test case where a pedestrian is crossing the road from left to right. You have a test case where the pedestrian is crossing the road from left to right, coming from behind a vehicle that's obscuring the pedestrian until the vehicle is closer. You have a situation where a pedestrian is standing in a road, and you have a situation where the pedestrian is walking in the direction of vehicle travel. So as most of you are probably familiar with the machine vision and AI, your ability to detect and classify an object is very dependent on the number of pixels that you have on the target. So really how much information you're able to extract from the scene. So it turns out in these test conditions, maybe the second test condition on the left, when the pedestrian is crossing the road, you have less of a profile and fewer pixels to detect on that pedestrian. So that turns out to be a pretty challenging situation. So here are some of the imagery at our test site at this center, American Center for Mobility near Detroit, where we conducted this testing. And on the left-hand side of the slide, you see the visible image. So we conducted this testing at night in what you would describe as a rural scene. So no street lights. This is consistent again with the FMVSS 127 test requirements. We used a high dynamic range visible camera. So essentially the thermal cameras, or the visible cameras, excuse me, that are used on vehicles today. That's basically gives you the best of visibility in a wide variety of lighting applications. And this is our automotive specific thermal camera. So you can see, even as we're beginning the test, way down the test track, you have no visibility of the pedestrian on the left with a visible camera or your eyes, but we're already able to see the pedestrian with the thermal camera, again, demonstrating the ability to see at night and the ability to have a very long range vision. Here, we're just showing you the imagery as we moved closer to the pedestrian. So again, near the start of the test, 45 meters away, it's very easy to identify the pedestrian on the thermal image at the bottom of the slide, the bottom left. In the upper left image on the slide, you don't see the pedestrian. And then as we get closer, somewhere between 35 and 25 meters, you're able to start to see, basically the lower part of the pedestrian, and by 15 meters, you're still able to see the lower part of the pedestrian. In this case, the top of the pedestrian is hard to see. And this shows how thermal cameras can detect the thing you most don't want to hit, which are people, very, very far away, allow the vehicle to gracefully slow and eventually stop. If you're only detecting a pedestrian tens of meters from the pedestrian, then you have a situation where you're slamming on the brakes, maybe you're avoiding the collision, maybe you're not, and you're creating a very unpleasant driving experience at the same time. So again, I think this illustrates, the additional information that a thermal camera can bring to a sensor fusion situation. These are some additional real-world situations. They're not specified in the FMVSS 127 testing, but for all of us who are interested in zero fatalities, they're very real-world oriented and very important. Here you can see a pedestrian on the left standing in front of a vehicle with headlights, very hard to see with the visible camera. Again, the thermal camera not affected, not sensing the lights from the vehicle, so very able to detect the pedestrian. This situation is a little bit more dramatic and could represent a downed motorcyclist or a bicyclist. So you can see in the thermal image on the right, there's actually a pedestrian that's laying horizontal in the roadway, and you're not able to see them with that high dynamic range camera on the left. We actually have some video of this scene, and it's a little bit dramatic, so I'll try to show it for you here. But in this case, we didn't use a soft pedestrian target, and this is a human-driven vehicle and an actual human laying in the roadway who'll get a little bit nervous as the vehicle approaches. But again, I think you get the point that even in this somewhat infrequent corner case of having a pedestrian in the middle of the road, you're able to see and detect them from quite a distance with the thermal camera. So how did we do overall? If you go back to those test requirements, those real world situations I showed you earlier, all of the test conditions are shown here. We tested in both day and night as NHTSA is requiring. We tested the crossing the road, walking in the path of the road, standing in the road. And the Teledyne FLIR vehicle with thermal, visible, and radar fusion, we were successfully able to pass all of the FMVSS 127 tests. So we think we've demonstrated that thermal imaging is definitely able to allow vehicles to pass these more stringent requirements and make roads and vehicles safer. The other vehicles, there have been some really significant improvements over the last several years as automatic emergency braking has improved, but all of the other vehicles ran into test conditions that they weren't able to pass. So a visible camera only system ran into troubles crossing with pedestrians crossing the road. And again, that's when you have fewer pixels on target to detect the pedestrian. The stereo vision had some trouble in situations at night, and similarly, the visible radar fused system had multiple cases. So we think these results demonstrate well the value that thermal imaging and thermal machine vision can bring to make the roads safer. If you're interested in getting more details, our full report on this testing and the work we're doing to make roads and vehicles safer with thermal machine vision, you can scan the barcode and it'll take you to a website where you can download our full report. And the other point we want to make is that, obviously this type of testing, uh, the targets, the things you're trying to detect have to mimic the real world as well. And so heated pedestrian targets are necessary to mimic the human profile and demonstrate the value that thermal imaging will bring to making vehicles safer.